Hi, my name is Song Min-hong, and I'm with Gwangju Institute of Science and Technology. The title of my talk today, Properties of Conductive Oxygen Vacancies and Compact Modeling of IV Characteristics in Hafnium Oxide RRAM. This work is first authored by my student, Mr. Junsung Park. Introduction. The Resistive Random Access Memory (RRAM) is a promising candidate of the future non-volatile memory. It has advantages in speed and endurance. Also, the CMOS integration is possible and the fabrication process is relatively simple. Moreover, it has been widely studied as a candidate for neuromorphic devices. The resistance of a metal insulator-metal junction determines the memory state. Among many possible materials, especially the hafnium oxide-based RRAMs are widely adopted. It can be successfully integrated into the modern CMOS technology. From the viewpoint of power, stability, and operation speed, the hafnium oxide-based RRAM exhibits superior performance. It is known that the conductive filament, a conduction path made of oxygen vacancies, determines the electrical properties of the RRAM. Therefore, it is very important to understand the change of a filament shape under a given operation condition. The simulation approach can be very helpful in this aspect. Various approaches with varying complexities have been reported. In this work, I want to briefly introduce our recent research effort on the hafnium oxide-based RRAM. First, the migration barrier of oxygen vacancies is calculated. In part 1, we have used the BASF packaging, an atomistic structure of an amorphous hafnium oxide system is shown. It is obtained by the DFT-MD optimization. In the cell optimization, the PB-SOR exchange correlation functional is used. In addition to an amorphous structure, a tetragonal supercell is also considered. Each structure has 108 atoms. The extended Frankel pair is a pair of an oxygen vacancy and an oxygen interstitial. Two defect types, an oxygen vacancy and the extended Frankel pair, are considered in this work. The migration barrier is the difference between the local minimum and maximum formation energies. In the tetragonal supercell shown on the left, the defect is generated at each symmetric position inside the unicell. However, for an amorphous structure, it is difficult to find symmetric positions. Therefore, we have manually selected possible defect positions. The migration barriers calculated in this way are shown in the figure. Field symbols are reserved for crystalline structure, and empty ones are for amorphous structures. They exhibit good qualitative agreement. The migration barrier of an oxygen vacancy is about 0.5 electron volt or 0.6 electron volt. On the other hand, the extended Frankel pair has much lower migration barrier, about 0.3 electron volt or 0.4 electron volt. Next, the electrical conductivity is calculated for oxygen vacancy filaments. In this time, extended load-like supercells are used, and the total number of atoms in the supercell is 296. By assuming the low electron-electron and electron-phonon interactions, the mode formula is used to calculate the resistivity. Here, conductivity tensor is obtained by using the linear response function of the fast packaging. Starting from the structures shown in the last slide, oxidation vacancies or extended Frankel pairs are introduced to make up filaments. The number varies from 2 to 8. Of course, when more vacancies are inserted, the conductivity becomes higher. Since the atomistic simulation model is much limited in its size, the defect density is unrealistically overestimated. The energy spectrum of the calculated conductivity is shown in the figure. For defect-free structure, no state is available in the forbidden zone. Therefore, the resistivity is extremely high. On the other hand, when vacancies are introduced, the defect sites in the forbidden zone are clearly observed. Those states contribute to the conductivity. The calculated resistivity is drawn as a function of the defect density. Each symbol represents a distinct sample. Amorphous samples have a relatively higher resistivity than the crystalline ones. When the number of oxidation vacancies increase from 2 to 8, the resistivity of the crystalline hafnium oxide increases more than 6 orders of magnitude. Although a direct comparison cannot be made, a good qualitative agreement is obtained with the experimental result in previous reports. Finally, an existing compact model is applied to generate the IV characteristics. We have adopted an existing compact model. In this model, the filament shape is simply characterized by a gap between the top electrode and the filament endpoint. It is denoted Z in the first equation, and its change is described by the second equation. Detailed description about parameters can be found in the reference. The compliance current implemented with an ideal MOSFET in the saturation mode. Transient simulation is performed to mimic the actual measurement setup. Fabrication process is sketched. The bottom electron is platinum and the top electrode is titanium. The thickness of the hafnium oxide layer is 15 nanometer. The measured IV characteristics at room temperature is shown. The compliance current is 10 milliampere. The set and reset voltages are 2.5 volt and minus 1.1 volt respectively. When measured at 0.1 volt, the HRS resistance is 13.6 kilo ohm and the RRS resistance is 48.5 ohm. The ratio is about 280. After calibration of parameters, the switching behaviors are calculated at various temperatures down to 250 Kelvin. For lower temperatures, the absolute values of the set and reset voltages increase as shown in the right figure. A similar trend can be found in a previous report. We have a plan for the low temperature measurement to further validate our calculation result. Let me conclude my talk. In this presentation, our recent research effort on the hafnium oxide-based RRAM are presented. The material modeling in part 1 and the compact modeling in part 2 will be combined with the KMC simulation. We hope that we can report it in the next year. This is acknowledgement, and thank you for your attention.